Thank you. How you all doing? All right, so yeah, I'm going to talk about programming a node cluster. And I think I just started researching on how, I typed in like node cluster to see what the current literature was out there. And I think I saw something about like, there's a cluster module that allowed you to distribute computation over all the cores in your CPU. And I think that was about all that I found. I heard about something called strong cluster, but I didn't really have too much time to look into that. So I hope that what I'm about to present isn't kind of already something someone's done. But in any case, I think I've got a few cool ideas that maybe some of you may or may not have familiarity with, and hopefully you'll find that valuable. So I work at Twitter. I work on the website there. I'm actually moving teams, but I spent this whole year working on the back end, the framework. And I kind of took a lot of the story around scaling from what I've seen at Twitter. Even though I don't really use JavaScript that much there, I think JavaScript's been a part of my whole career as a programmer, and I'm sure that's the case with many of you. I think we're all drawn to JavaScript because it makes it really easy to build things. For example, this is an echo server in 2 lines of code, which is pretty amazing considering what you need to type in other languages to get something that does the same thing. It's using pipes, so thank God for that last talk, otherwise people would be like, what's that, right? So what's happening here, just to explain it a little, is create server, I think what it does is basically opens up a TCP socket, binds it to an address, and starts calling accept on that socket with each new returned socket from accept. So accept basically is the master server socket. And any clients that connect to this server, like on port 8000, they'll get turned into a client socket and passed into that callback. So it'll be C is basically a handle to the client socket. And what we're doing is just piping the output back into its input. So we're just echoing back. So that's pretty amazing. It's pretty simple. I think it is a great example of JavaScript's simplicity and how it makes things easy to build. But wouldn't it be great if everything stayed this simple as our server grew, as our applications required us to scale them, build more things into them? And I think that story is what sort of drove me down this road. So what's difficult about growth? I mean, there's a lot of complexity that comes with. Well, if we just examine this code, what are the limits that we'll encounter pretty much immediately when we go from, let's say, 100 connections to, let's say, 100,000? Like, we'll start encountering the limits of the hardware that this code is running on. So there are a couple of ways to sort of distribute that load. And like I mentioned previously or earlier about cluster, there's a way to distribute the computational load across cores, which you can imagine if there was some sort of some call that you could make fork, which sort of spins up a new thread or process, like an OS level thread that you could pass into, or the runtime would take care of passing that callback into it and running that on a separate thread so that things don't just run concurrently, but they actually run simultaneously. You could do that with the fork command. Now, if create server, and I believe create server could be smart about this, it could also pre-fork. So inside of create server, we could call fork And for as many cores as we have on that machine, we would just fork that many threads to handle the accept. So what happens here, actually? It's really interesting, because a lot of servers are built like this, sort of in the last decade. All of these connections, these master sockets, they all point to the same thing. And every thread is waiting on accept. And what happens is, when the first client tries to connect to this server, only one of those accepts would succeed and the rest would fail. I think OS kernels are smarter about this these days, and will schedule it such that they'll only wake up one accept call, so that there's no, so that they don't wake up all the threads and have this sort of like thundering herd problem. So that's called preforking. So if we've reached the limits of that one machine and all the cores on that one machine, we'll soon have to start distributing load across hosts, across multiple machines. And when I had a look at what was out there to solve this, there wasn't really much I found in the Node standard library. Other languages have some things. Akka for Scala, which is inspired by Erlang. Distributed process in Cloud Haskell, also inspired by Erlang. So what's special about Erlang? Why is everyone being inspired by it? Like, what's the difference in that model that other people aren't using? So going down that road, I think one question to ask is, well, why do we even need another abstraction for this, even though this is amazingly simple? Maybe that's really all we need. Maybe we can just scale it. Maybe we can scale this application in the traditional way every application is scaled. And if we look at how small systems grow into large ones, usually start with some sort of client server. There's no legend here, so you're going to have to use your imagination, I'm afraid. One of the nodes is a client. One of them is a server. And if you just look in the top left, we'll move downward and to the right. So client-server topology, so simple. You have one client, you have one server, or you can have multiple clients, actually, and just one server. And this works really well, especially if one server can handle all the capacity of your requests. Usually they can't after a certain size, so if we move down into the right one, you'll see that there are many clients now. We're load balancing them through a proxy, that green circle, to multiple backends, or front ends, whatever. So you can see it's sort of getting a little bit more complicated. And I think this progression leads us downward and to the right to this topology in the end, where you end up having to, if you're proxying all your traffic through that green circle, the load balancing proxy, that becomes your bottleneck. And so what people end up doing is creating a discovery service. So down at the right side, the green circle is a discovery service that the client nodes and the server nodes have to connect to and figure out where everyone is. So this is required because let's say you have a server cluster that nodes are like coming up and down. So let's say you want to keep it elastic, and as traffic comes in, you want to add 10 more nodes or something. You'll have to have all your server nodes inform the discovery service that, hey, I'm available for taking traffic now. And then that discovery service will then inform all the clients and say, hey, this is additional capacity that you can use. Likewise, if nodes go down, then the clients will end up being notified as well. So this is one of the complexity that you have when you grow from a small to a big system. And I want to say that some of this complexity is totally essential to the problem. Like, you cannot escape having to share state, for one. But I think some of the complexity is completely incidental to the approach that we've chosen to scale. So we initially went down this path because we wanted to grow our service to take on a number of requests that were growing. And I think it led us here because, well, we don't have the right abstractions to handle distributed programming. So what would those look like if we wanted to build them? I think we need to understand the problem a little bit deeper. So the essential idea in its most abstract is that there are two kinds of topologies. One is this two-entity topology, which is the simplest one. You have a client and a server that are communicating. And it only really gets complicated when you add a third entity there. And you can kind of think about it like this, like in terms of a dependency graph. If you modify in the two-entity model, if you modify one of the nodes, either the server side or the client side, you'll only have one other thing to update and modify to be in sync, whether it's like a protocol or a data structure. But if you have a three-entity model here, basically everything needs to change if one of them gets updated. And I'll try to give you something more concrete, because I know this is a little bit like use your imagination. So let's have a look at state. See, in this two-entity model, the state only exists in one node, in one place. But with the three-entity model, what we're doing is we're trying to distribute some state around because we think it's more scalable. So what kind of ways do we have to do that? Well, there's shared memory. So shared memory is something that, well, like if you were just running on one machine and you spun up a number of threads to deal with, like to distribute your computational load over, you could use shared memory and have each thread communicate to each other without really exiting the runtime. But once you have to distribute your load across machines, then you need to have something that different machines can access. And you can't, I don't know if you can share memory, like maybe there's an OS level way of doing this, but sort of like if you have two machines across the network, can they communicate can they share memory? I don't know if there's such a thing. But they can communicate through a database or some key value store or a message queue. So you have two primitives here. You have one that allows you to communicate thread per thread, from thread to thread, and another one where you can communicate from machine to machine. But these are pretty low level. What we're essentially saying here is that we can take that model we used for shared memory and put it into a data store across a network to scale. And it will be kind of the same. Functionally it is, but I want to draw attention to why we initially came, like what drew me to JavaScript at least was the ease of building things, the two-line echo server. And I want to say that when we move from a model using shared memory to coordinate threads to distributed to a data store, it makes it harder to build things. I tried to build I was building a chat server recently, and one of the things I saw was when we went from a model that had just two entities to one that was mediated via a message queue, we encountered friction in these three ways. First thing that we lost was an implicit session that was tied to the TCP connection. So if you have a chat client connected to a chat server directly, what the next, like other chat clients can do is they can message each other through like sharing the same data structures. For example, like if you have Alice and Bob connect to a chat server, Alice basically puts a message in Bob's data structure for his whatever queue that's waiting to write out to Bob's chat client. Once you have a database doing that, so if you have Alice connected to one server and Bob connected to another machine, and they have to coordinate through a data store, you lose this session. Sorry, I think I'm confusing myself because of, I guess, how. The session that you lose is when Alice tries to, I think, connect to different nodes. So Alice has two clients, and if you have a request-response mechanism, what will happen is the first request will go to one server node, and then the second request will go to the other one. And there's no way to sort of figure out that they both came from Alice unless you also tag a session ID in that request. So when we try to maintain a session across browser contexts, we have a cookie and like a session store. That's exactly the same problem we're trying to figure out. We lose that because if we didn't have a distributed model, then we would know that a connection to Alice always had Alice's context with it. The ownership of a mailbox is something that we also lose because we don't really, if we went from the left one to the right, let's say one of the servers deposited a message for one of the clients, but then another client somehow read that mailbox that they weren't supposed to. So you have to sort of manually figure out permissions, like which client is allowed to read off which queue. And sometimes that's not built into a data store. You can just sort of read from anything or write to anything. And then the third thing that sort of you lose when you scale out this way is multiple recipients. So imagine if Alice is connected to the chat server. Let's say it's a browser. Let's say you open two tabs. So you have like two connections now to this chat server, but they all correspond to the same logical client. If we were using that first model, we could just say, oh, Alice has connected in these two connections. We'll just send two. So if like Bob messages Alice, we'll just send two messages to Alice. Because Alice has two connections, because the server knows that these connections are correlated. But once we have distributed this application across multiple servers, and we have a message queue that's in the middle, how are the servers going to know how many messages to put on the queue for Alice? Let's say she has two devices that are connected. One device will find one message, but then the next will it pull two, how many times do you need to write to this queue so that the devices on Alice's side can like pull out the right information so that all devices like have all the messages and they don't get dropped? So there are ways around this. It's just what it does is it creates friction around writing the chat client, around writing the chat server. The thing that we use to scale out and grow is the very thing that creates friction so that it slows growth. And I think this is sort of the heart of the matter here that like disturbs me the most. So like what's really happening? Let's say we can just do away with the message queue. Can we synchronize it by allowing the servers to talk to each other? And that's sort of what I've been trying to get at with this experiment that I'm going to show you just in a bit. So what we have here is we have shared state. We had two primitives for this. One is to share memory between threads. Another is to share data between machines. But then with this model here, we don't have to share anything. And this is the heart of message passing and the actor model, which I'll try to explain as clearly as I can. So has anyone heard of the actor model before? So a bunch of you. Is it fair to say that this is how it might look in JavaScript? So an actor is essentially a function that has some initial state. And it has two things, two commands that can be sort of invoked on it. One is you can expect a message. So an actor can expect something to be sent to it. And given a handle on an actor, you can any process can send messages to it. So expect and send. So expect takes a callback. When this actor is sent a message, it runs that callback. It's pretty clear. So imagine an actor that sums things, starting with an initial state, let's say 0. And then any message that gets sent to it, it just takes its initial state and adds that message if it's a number. I put in another command here, get, so that another process could examine the internal state of this actor. But let's just focus on the sum function first. So we expect something to be sent to the mailbox of this actor. If it's of type number, then what we do is we call sum again. We recurse with a new state, the state plus this number. So we end up at the top of the function again. And then we're waiting on expect one more time. However, if it is an object with a command property that equals get, then what we do is we don't recurse. In fact, we just bail out. But what we do send is the sender of this message, which is another actor. We send them our state. I hope that makes sense. So this is how you could run that. Imagine that there's such a thing called actor that takes in this particular actor definition, sum, with an initial state. So the first actor, A, has an initial state of 0, and B has an initial state of 12. And you can send them both some messages. And then remember that the actors can communicate with each other through message passing. So what we need is another actor, a printer, that can send A the command get so that A can send back its state, which will be printed out. So what happens is we completely ignore B's state. Could anyone sort of guess what could get printed out right at the end here? It'd be an initial state 0 plus what we sent it, which was 1. So it should print out 1. And that's the logic of how these actors go. The problem here is that this is still not distributed across machines. If you look at message.sender, that's an instance of an actor. And you can't send that across the wire. But what we could do is we could have IDs for each actor and a lookup table that matches a particular ID to an instance of that running actor. So what we need to change is we need to send the ID instead of sending the actor. And instead of having, it looks like I didn't update that, but it should really be send, which takes an ID, and then the message to send. So if you can just imagine that I changed that. The implementation that I came up with had each process ID, each actor ID, have a URL, because we're assuming that this is going to be distributed across a number of machines. So you could have one server running on port 3000 and another server running on some other IP address, port 4000. And each of these instances of servers had a bunch of processes that they could correlate with the ID after the /. So what would happen here is the send method would try to figure out, all right, which connection do I have open that can reach localhost 3000? And if it doesn't have a connection open, then I'll create one. And then over that connection, I'm going to send a message to the process that is running on that host, identified by 123. So that's what that is. So this is how a process could look. This actually works, by the way, but it has a little bit of a different interface than I've been showing you, because what I did was I think I wrote this a long time ago, and then last night I was thinking, oh, you know, it could be a lot better if it was just function calls. So the process here is an actor. And the only thing that's different is we create these send and expect methods on this actor, on this process. And you can see that the mailbox is the queue that sort of is in between each, send and expect. So when you send something and there's nothing, this process isn't expecting anything, it sort of just goes in the queue. And it's like a first in, first out queue. The next call to expect will grab something off that queue. Yeah. So what I want to show you is an example with ping. What we have here is we have two processes. One is the ping actor that will respond to a ping with a pong message, and the master process that will actually send the ping or receive that pong message. So we're saying that ping expects a message of type ping. At the bottom, we actually send it type ping, and we say this is from the master process. And inside of ping, we have we take the message.from, which would have the master process, and we send that a pong message. So you then end up, with that message printed. Let me just show you how that actually looks. So, so it's sort of, this is the code, but you should realize that this is still not, distributed across machines. I have some code that actually is distributed across machines. And you can see here that we have a server and a closure structure. The most interesting thing, I think, is the slave or the worker nodes start a server. And I think I could have this on the slides, but just in case I don't. Basically, every worker node listens to commands, and if it receives a spawn command, spwn here, what it does is it calls that process. It creates that process, puts it up in the lookup table, and whenever it receives messages for that process, it just sort of proxies it to that running process. So this actually works. Let me just slave. Let's say I'm running that on 3000. And another one here. And I want to create a master node that will ping both of them. So it's pretty much like that. They both get the pings. And these could be running across the network, but they're just running locally, incidentally. Anyway, I'm going to skip through these because you just saw that. Multiple ping distributed. So let me just close with this. You've seen how to scale, how the typical story of scaling, where it leads to. And I think that we have an alternative model that we can use. Imagine if we had something called distributed.createServer that creates like a master node and a worker node, and we could just create a distributed ping server like this. I think if we write the distributed programming story this way, we can find ourselves back to a place where things start looking like they're easy again. And that's kind of all I have for you. Thanks for listening.